Alright, so today we're going to talk about partial derivatives. And so to give you an idea, we're going to draw a little bit of a picture here, but we're not going to do it in 2 dimensions. We're going to start in 3 dimensions. We're going to put our x-axis here, our y-axis here, and our z-axis here. So let's label them x, y, z. And let's say that we have a curve, or now it's a surface rather. Let's say we have something that comes up here, but let's say it's in 3D. Like so. Alright, so we have that surface there, and of course this is not just flat, it's going around like so. Just so we're very clear. Alright, so let's say now we want to find the derivative at a point on this surface, just as we did before. Let's say you start here. Now we have a problem. Not a problem, but we have a little bit of a difference from what we had before in the 1-dimensional or 2-dimensional case. And that is that we don't have a tangent line, but we have a tangent plane. So you can put a plane that will be tangent to the surface at that point. And the question is, how do you compute the derivative? And what does it mean to compute the derivative? So what I can do is say, well, I can go in the direction of one of the axes. So for example, I could go in the direction of y. So go in the direction of y and see how my vector is going. And I would get a vector that goes kind of there. Or I can go in the direction of x and I have a vector that goes kind of here. So it gives me, at least I have 2 possibilities. If I go in the direction of y, what I would be doing is looking at how the function is changing as I move in the y coordinate while x is being fixed. So what that would give me, and I'm going to do an interesting sign here for the derivative. And let's say this, by the way, this graph would be the graph of z that is a function of x and y. So whenever I am trying to compute the derivative of f in the direction, or with respect to y, in the direction of y, I'm going to say that this is going to be the limit as h goes to, my bad, let me erase that. H goes to 0 of f of x comma y plus h minus f of x comma y, and I did it again that I don't respect my division there, all over h. So what you're doing is you're looking at the change in the y coordinate by leaving your x fixed right there. And if you wanted to look at the change with respect to x, you would do the same thing. Alright, a little bit smaller there so I can fit it. Limit as h goes to 0 of f of x plus h, leaving y fixed, minus f of x comma y, all over h. So that would be, and we use this curly because they're going to be partial derivatives. Why do we say they're partial? Well, because we are leaving one of the 2 variables fixed. So how does that look in practice? So this explanation is a bit of overkill when you see how you compute it, because when you compute it, it's extremely easy. So let's do an example. Let's start with something very simple. First, let's say that your function is going to be z equals f of x comma y, where f of x comma y is going to be given by, say, 1 minus x squared minus y squared. Alright? So at that point, if you want to compute the first derivative with respect to y, partial derivative with respect to y, what you would do is you take the derivative of this. Alright, let's start. Derivative of 1 with respect to y, 0, because 1 is a constant. So I'm going to write it out in detail, but you don't need to. Derivative of x squared with respect to y. Well, x does not depend on y. X is an independent variable, right here. So that means you're going to leave this guy fixed. This is a constant. When you take that derivative of a constant, you get another 0. And when you take the derivative with respect to y, well, you do get 2 times y. So your partial with respect to, I guess I forgot a negative, negative 2y. Your partial with respect to y is negative 2y. So what did I do? Whenever I saw an x, I just treated it as a constant. So let's do the partial with respect to x. So it looks fancy and all, but it's really easy. Derivative with respect to x of 1 is a constant, 0. Derivative with respect to x of x squared, well, right here we get negative 2x. And then derivative with respect to x of the y, that is going to be 0. So just like that, you consider your other variable a constant. All right. So let's do a couple more examples, and then I'll give you a little bit of an intuition as to what is the difference between partial derivatives and implicit differentiation. Because if you remember, we took derivatives that involve y's or equations that involved x and y, and you may be wondering, why is this any different, or what is the difference between them? So we're going to talk about that as well. But let's compute a couple more examples first. Okay, so let's say I want to compute the derivative of z equals sine of x squared plus y squared. Something like that, for example. So what would be the partial with respect to x? Well, you take the derivative of this term right here, and again, now you gotta do chain rule because you have a function of x and y in here. So you take the derivative of your sine, you get cosine. And now you multiply times the derivative with respect to x of the inside. So the same thing you would have done for your chain rule before, you're doing the same. Because remember, the definition is pretty much the same. If x is fixed, then whenever you prove the chain rule, you get it as well for the chain rule for ordinary derivatives, you get it for partial derivatives. So there's no difference there. You still have to do chain rule. Perhaps unfortunate for some people. So taking the derivative of x squared plus y squared, you get the derivative here with respect to x of x squared. I'm going to put it in the front. Let's start with that. 2x plus the partial with respect to x of y squared. Y squared is a constant when considered with respect to x. Derivative is 0. So the derivative of this is just 2x. And then I multiply times what I had, cosine of x squared plus y squared. Now, by symmetry, you can see this is symmetric with respect to the axis, so you could replace x and y and nothing changes. So you will see that your derivative will be the same, except, x changes to y. My bad. So let's change it out to 2y cosine of x squared plus y squared. Alright, so that is another example where you have to do chain rule. Let's do one where you have to do, for example, product rule. Example. That was weird. Alright, so let's do one where you get z, and we're going to do a product rule, for example. So let's do x plus y times x squared minus y squared. Of course, you could FOIL that out and, actually it's too easy. Let's put a cube, just so we can do something a little bit more exciting. But you could FOIL it out still and compute it directly, but let's use our properties of differentiation. Let's do the partial with respect to x. So again, you have a product, so you start with product rule. So you get derivative of the first, which is this guy, is going to be with respect to x. So right here, partial of x with respect to x is 1, times plus partial with respect to x of y, that's 0, because we're considering this one is a constant, times the second, plus, then you're going to copy the first, and then take derivative of this one. So derivative of this one with respect to x. So I'm going to drop a 3. How am I doing? With space a little bit tight there. Copy the inside. And then subtract 1. So 2, and that's as much as I can fit, times the derivative of the inside with respect to x. So with respect to x, the derivative there is going to be just 2x. And then derivative of y with respect to x is 0, so you close your parentheses there. So let's reorganize it a little bit and write it all. We could, of course, try to simplify by factoring that x squared minus y squared up front. Let's do that. That's going to make our computation a bit easy. Or simplification, rather. And then I'm going to have 1 left over here, because I had 3, I took 2. I'm left with 1. And then here I took one of them. This 2 is gone. Or these 2 are gone, rather. I have a 3 times 2, so it's going to be 6x, 3 times 2 times x, 6x times still x plus y. You could simplify further by doing x squared plus 6x squared is going to be 7x squared. You're going to have 7x squared plus 6xy minus y squared, but that's good enough. That's just algebra we're missing. We're going to leave it at that for this one because I don't have room for the partial with respect to y, but the process is the same. So that's how you do partial derivatives. Whenever you're taking a partial derivative with respect to x, you leave y fixed. You consider it a constant. Whenever y appears, it's just a constant. And if you're taking the partial with respect to x or y rather, then x becomes a constant for you. All right. Now let's talk about how is implicit differentiation any different from partial derivative. So let me erase this and we'll talk about it in 1 minute. All right. So now let's talk about implicit differentiation versus partial derivatives. So remember what we had in implicit differentiation, and I'm going to use an easy example. So let's say something like this. With implicit differentiation, what we were doing was taking the derivative of this whole thing with respect to x, but we're taking the ordinary derivative because we were assuming, and rightly so here, we can solve for y. We could assume, or we're assuming that y was a function of x. Then whenever we're taking the derivative, we had 2x minus, you have a product rule here, derivative of 2x is going to be 2 times y, minus again, because you have to distribute that minus, derivative of this with respect to y is going to be 2x times dy dx. And then we solved, right? That was how we did our implicit differentiation. So this right here is our implicit differentiation. But that was the key back then. We were assuming that y was a function of x. What we're doing now is we're saying that x and y are both independent variables. And when you take the derivative, say you write z equal to x squared minus 2xy, the same function on left hand side here and on right hand side here. But what we're saying now is that we're looking at how this function z is changing with respect to x. And in this case, x and y are independent variables. Z is a dependent variable. Back here in implicit differentiation, x was your independent variable. Y was dependent on x, or you were assuming that there was a dependence. And in this case, then, your partial with respect to x would be just the 2x minus 2y. So compare the term that you're missing, or you're off here by, is this one. Well, the negative as well, but that term is what you had the difference. And why is it different? Well, because this right here is telling you how this expression changes. This expression changes with respect to y when y is a function of x. But in this case, that term is missing because y is not a function of x, so there's no dependency and this term disappears. So that is why, or that's what is different. Whenever you're doing a implicit differentiation, you're assuming there is a dependence relation there. And whenever you're doing partial derivatives, you're assuming they both are independent. As such, the term that captures the dependence of y and x is gone. So that is the difference between partial differentiation and implicit differentiation. Here also you're taking the ordinary derivative. Here you're taking a different derivative, which is our partial derivative. Both definitions are somewhat the same, except now the function is in two variables in this case, as opposed to here where you had only independent variable was x. So that is where you have, that is the difference between those two. Or one more comment. A lot of people have issues whenever you have a product like this, whenever you're computing a partial with respect to one of them. So whenever you have something like that, let's do one quick example. If you're taking the partial derivative with respect to x of a term that has a 2y squared x cubed, not in the right order, but it's okay. When you're taking the partial with respect to x, what you do is you take this whole thing. It's kind of nice that I put it there because that whole thing is going to be considered a constant. So this right here is the same as if you had just 3x cubed. Doesn't matter. You take it as a constant. And then when you have it as a constant, then you just copy it. And then you take the derivative of the term that involves the x, which gives you a 3x squared. And when you multiply, you get 6x squared y squared just by flipping them. And that is how you take your partial derivative. If you were to do implicit differentiation, it would have been different, right? You would have had this term, and then you would have had another term for y x cubed dy dx, because you would be capturing that dependence right there. All right, that's going to be it for this video, guys. I hope to see you next time.